Section 14.1 is the beginning of characteristics of light. Okay, characteristics of light. James, you asked a question the other day. Why aren't we doing chapter 13, correct? Was that you that asked? Was you? I thought it was James. All right. The honest reason, two things. One, the SAT subject test, which I'm trying to get through most of the material that's on there, really minimally covers that. And I put a little add-on at the bottom of Moodle for SAT subject topics that we didn't cover. And then all they talk about really there is how sound waves work and then the Doppler effect. There's not much more to it than that. And the whole chapter goes into a lot of detail about sound waves. So I don't go into a lot of it. I put a video on the Doppler effect at the bottom of the Moodle page. You'll see it at the bottom there as well. So if you want to read. But that's the major reason I don't go to 14. You'll see we're going to jump around even from this point on. There's going to be sections we're going to cut out. Like we're doing 14.1 today. And then I think we do 14.2 and 14.4 together next. I think I lumped. And I just cut out 14.3. Again, simply because some of the material that's on there is not stuff that's aligned to that test. And I want you to be able to at least take that test if you want to take something at the end of the year. Because you can't take an AP test, but at least you could try to take the subject test in physics. Okay? Nick?
Subject test, don't you need to have the formulas memorized?
Yeah, that's what I told you in the beginning of the year. So that formula sheet that I give you is not provided on the subject test for physics. So formulas need to be memorized just to even take the test. Or else you're just going to be lost, to be honest. James?
Would you be allowed to do
Would you what?
Would you be allowed when you get to the test to just do a formula, all the formulas under part of the test?
You could write all over the test. Yeah, absolutely.
So I could just write, literally copy from memory.
Sure. Absolutely. Okay? But they're not going to be really elaborate ones. Like some of the formulas that we go into that are much more complex, you'll see later in the year with electricity and magnetism. It's going to be the basic stuff. And if there are a few on the test that they give you, they might say well, the formula for finding the electric field between two charged particles is F equals K Q1 Q2 over R squared. They might give you a few of them on the test and then ask you, what happens if the charged particles double in charge? And that's where you have to find that relationship. Oh, it increases by a factor of 2 or a factor of 4, whatever we've been doing, that kind of stuff. They give a lot of those kinds of questions on the subject test as well. Okay? But there's a good amount of material that's on there that we still don't have time to get to. So if you are considering taking it, you should already begin studying. You should really begin studying maybe from mid-semester on or mid-year on. Okay, so after semester 1. So if you are considering it, I would recommend that you make sure to get a book and then look at the links I put at the bottom of Moodle. Okay, there's a bunch of extra stuff down there.
When is the actual subject test?
It's up to you. Take it. It's offered almost every month except for 2 or 3 months out of the year. But the one I would suggest is the one after the school year is over. So I think there's one in June. There might also be one in July. I'm not sure about July though. You can look it up. But I would not encourage May. We wouldn't finish everything and you'd be too busy with finals and stuff. But maybe the one in June. Although June you have finals as well, right at the beginning of June. So.
No, we get out. Yeah, we get out.
Oh, this year last day is May 30th? All right, so never mind. So then the June would probably be best. It's probably June 9th or something. Okay, but there's a lot of studying you have to do it. It's probably the hardest subject test there is for SAT. People always say that. Okay, so I'm telling you now, you really do need to study. It's not going to be if you just do everything from class, you're going to do well. There's additional stuff, and there's a little bit more complicated stuff on there. So you need to get a practice book. You need to go through it. You can come see me if you want help on that stuff. I'm happy to. So if you're having troubles on studying out the practice book, just bring it in for office hours and ask me. Okay? All right, let's get back to 14.1. That was a bit of a side note. So we're going to do 4 things. Again, we're starting. Chapter 14 is all about the EM spectrum and light. Okay, so we're going to look at first the components of the EM spectrum, EM standing for electromagnetic. We're going to recognize that light has a finite speed. It has a finite speed. Finite means what? Yeah, no. Oh, limited, good. Yeah, limited speed. Limited speed, not unlimited. Limited speed. We're going to describe how the brightness of a light source is affected by distance. And then we're going to look at some calculations to look at wavelength and frequency. So for example, we'll talk about those radio waves that we mentioned quickly in our last class. We'll talk about gamma waves. We'll talk about anything that's on the EM spectrum and how those waves are represented by their wavelength or frequency. Okay? All right, let's take a line. The electromagnetic wave, first, it's a transverse wave that consists of oscillating electric and magnetic fields that are at right angles. And this is difficult to see just by looking at it. But if you look at the yellow arrows are representing the electric field. And I'm going to follow it with my cursor here. So this is the oscillating electric field that you're seeing. Okay, that's the oscillating electric field there, right here around this yellow wave. The magnetic field that oscillates is at a right angle to that. And that's this right here. Okay, that's this line right here that's following along. The actual direction of the wave is perpendicular to both of these, thus it is a transverse wave. Transverse wave. What did we say sound was? What kind of wave is sound? What was the other one? Not transverse, but come on, people, we did this like yesterday. L.
Oh,
Longitudinal.
Longitudinal. Remember, longitudinal, the vibrations move in the same motion as the wave itself. When I talk, the molecules vibrate towards your ear. They're moving in the same direction. It was like the slinky when you did this. And the slinky compressed around the whole way and then came back. But these are magnetic and electric fields that are moving perpendicular or transverse to the direction, this red line, the direction of the EM wave itself. So this is a transverse wave. Okay, a transverse wave. Examples of EM waves. There are a lot. You do not need to memorize this. You do not need to memorize this, but you do need to know that there are different types of waves for sure. So let's start in the beginning. We're going to go through each of these. Okay, we're going to take a look at each of them. First, yeah.
Wait, sorry, I just have a question there. I forgot to ask the listener. You have a problem with
Lambda?
Lambda, yeah. If it gives you nanometers, you have to convert it. It's like 8 decimal places.
Yeah, it's times 10 to the negative 9 for nano. Times 10 to the negative 9.
I did that one somewhere. I didn't know if I was supposed to.
Yeah, I would use my calculator to do those kinds of conversions from this point on. I would not start moving decimals because you're going to get numbers that are on the order of 10 to the 25th. Like, look here. Look at the frequency range of gamma rays. They're 10 to the 22nd hertz. So I would start using scientific notation a lot on my calculator at this point if you haven't done so this year already. Okay?
Look at you.
Yeah, using the second EE button. Yeah. All right, let's start with radio waves. Radio waves have the largest wavelength. Take a look at their wavelength. They're greater than 30 centimeters. Greater than 30 centimeters. 30 centimeters. That's a third of a meter. That's a long wavelength for an EM wave. Look down at the bottom of gamma rays. Look at their wavelengths. They're between 0.1 nanometers and 10 to the negative 5 nanometers. We're talking about things like 0.001 meters. 10 to the negative 5 nanometers is so small, it's unbelievable. So these are small, so write this down, please. These are small wavelengths at the bottom, and the top is large wavelengths. And what do you know about wavelength and frequency? How are they related?
Smaller wavelength, greater frequency.
So we say they are what related? What is it? Inversely related.
Oh, yeah.
You said right, the smaller the wavelength, the larger the frequency. Take a look, please. The large wavelengths at the top here have very small frequencies. Look at these frequencies at the bottom. They're on the order of 10 to the 18 and 10 to the 22nd. At the top, it's only on the order of 10 to the 9. And what did you notice I told you? Last class, your radio stations are megahertz, right? Remember we talked about megahertz real quick? So if you tune into 100.3, okay, which I know a lot of you listen to is Z100, it's really megahertz. What does mega mean again? Times 10 to the?
Negative 9, 6.
Positive 6. So this is really 100 times 10 to the 6. Well, if I move that over here, we're going to get 1.003 times 10 to the 8. And take a look. The frequency has to be less than 1 times 10 to the 9 hertz. And indeed, radio waves are less than that value. But the radio waves you see advertised on your stereo system or whatever it is are with units of megahertz, right? Megahertz. Now, as we go down, we're going to see that we go from small frequencies to large frequencies. So these are small frequencies, and we used omega, not F. Let's use omega. Okay, and down here, we have omega values that are large. Let's talk about each of these and talk about some applications. And I want to get your input here. So obviously radio waves, AM, FM, television. What about the next one? Microwaves. And remember we talked about why the microwave was named the microwave? Here you go. This is it.
Wi-Fi is also a microwave.
Say again?
Wi-Fi is a microwave.
Is it on the order of 10 to the -6?
Whatever it is classified as a microwave. The actual emission from it.
What, like a microwave to heat up food?
I mean, I'm not sure, James, to be completely honest.
No, I looked it up last night. That's what I got from the last person. I was interested in that because I was like, really, that doesn't cause any bothering on.
I know that you're not supposed to like stand next to your microwave for a while because of the radiation that you can get from it or the microwaves you get from
Like,
it.
doesn't
Watch.
doesn't
Yeah,
the
but you have to
doesn't the
have that.
wavelength of each microwave kind of vary that effect of like? intensity?
Well, it's between 30 centimeters and it looks like a millimeter, right?
Yeah. So wouldn't like where it is along that tiny like spectrum change things? For
Absolutely. Absolutely, yeah. So what James is mentioning is this. The EM spectrum, notice, the wavelengths from here down to here are getting smaller and smaller, but each of these have a range. Look at the range of wavelengths you can have for a microwave. It can be between as large as 30 centimeters, as small as a millimeter. Then infrared is as large as a millimeter, as small as 700 nanometers. So each of these have their own like little mini spectrum. So what he's talking about is this. If you were to draw the EM spectrum here, this is like radio, has its own portion. Micro has its own portion. Infrared. Then this is what we see. Visible. Then UV, and this is not drawn to scale, obviously. Then X-rays. And then gamma.
Would a gamma ray kill you?
Gamma rays are types of things that, well, it depends on what type. But gamma rays are not healthy for human bodies, but they can help for things like food. And that's what they're talking about here, to get rid of radiation in food. There's different types of cancer treatment. If they're low enough dosage, I don't know too much about the bio behind it for human beings. But I know that gamma rays are used for cancer treatment. Okay?
What like makes it dangerous? I understand.
Anybody know a lot about gamma rays and how it affects the body? What makes it really dangerous?
Well, like how any wave really, like what makes it wave dangerous?
Well, radio waves aren't going to affect you.
All I know is that in terms of
Infrared waves are not going to affect you. Visible light won't affect you. UV does. UV changes your cells. It causes your cells to morph. That gives you cancer. X-rays after a long enough time will hurt you, but I'm not sure about why X-rays hurt you.
Is which one?
Yeah.
Black light. Is that what?
I don't know. Could somebody check that real quick? Somebody Google. What is the wavelength of a black light? Or what portion of the EM spectrum does black light fall into?
black light was just like a regular light. Yeah.
It's a fluorescent. It pulls fluorescence out, but I don't know. Try to find. I mean, it's clearly visible light because we can see it, but I wonder where it is in the visible light spectrum. Because remember, visible light is Roy G. Biv. The large wavelengths are red, the smallest wavelengths are violet, and they range in between. I don't know where it is in there.
I don't understand what the lambda and then they have hertz. What?
Lambda's wavelength. F, in this case, is frequency. This is omega here. Wavelength, frequency.
Apparently black lights emit violet, visible light, and ultraviolet light
Okay.
simultaneously.
That makes sense. So it's on the lower end of the wavelength spectrum. And take a look. Right at 400 nanometers, you have violet light, but anything just less than 400 nanometers becomes ultraviolet. So it's probably a combination of those two. But it's not going to be UV rays that can hurt you. Remember, there are UV rays like UVA, UVB, okay, different things. Let's just quickly go through the applications. So microwaves, you look at radar, molecular research. Aircraft navigation is, again, like radar, same thing, and microwave ovens. IR waves, infrared. What do you usually see infrared?
Lasers. Heat, like tripwires, like little secret agents.
Okay. Yeah, but it's usually a measurement of
Heat.
heat. It's like a thermal imagery. Okay? When you see infrared, we're talking about heat.
That's the vibration.
The person's molecules are vibrating at a certain frequency. And based on the vibration or the motion of the molecules, it's a measurement of heat. Your temperature is really the average kinetic energy of the molecules, and kinetic energy is motion. So if your molecules are moving more, you have a higher temperature. That's what's happening. So the IR waves are measuring the molecular vibration. And as a result of that, it gives you like a color. If you've ever seen like a military movie or a movie where they're wearing the IR cameras, they pull them down and suddenly they see like the heat from the body. They see like 3 or 4 bodies behind that wall. That's what they're using there. James.
What snakes can do that too. Some snakes can. They have like I forget what this organ is called, but adders have like a hole in their face that can detect IR light, and they can use that to see heat.
That's interesting. I didn't know that.
What you mean like Call of Duty?
That's what I meant for Call of Duty and stuff. Yeah.
They're almost
That's cool. I'm sure there was, I forget what it was, but there was another, I forget what animal or bird it was, but there was something to do with using certain waves besides a bat we talked about with the sonic waves and stuff, and using sound waves to find out its locations. But I read something the other day online. But that's cool. I never knew about a snake. Jordan?
Another application of infrared physical therapy. I remember when I broke my ankle, I was in physical therapy. They tried out the new infrared thing where they kind of like lasered my ankle for a little bit. And it was like a warm feeling.
I've had that done to me before with physical therapy where they put like a node and sent an electrical current through it.
Yeah.
Was it like that?
No,
What was it?
literally like a laser, like a red dot laser, like you know, that you see like
Yeah.
an hour. It was like that.
And it was pinpointed on the location of the
Yeah, and
break or whatever it
Yeah,
was?
it was going around the location. It was great.
That's cool. I never heard of that. Nice. And that's physical therapy up there. Good point.
Yeah, when I tore something in my hip, and then they had to put cream on it, and then like put this laser on it, and then they also put these like suction cup things, and they press this thing and go through.
Interesting. I never knew about that. I read it last year, but I never knew anybody actually went through that.
When I broke my wrist, they did a similar thing, but it was like when I had the cast on, they would put something on, it would set like electric pulses through, and it would speed up the healing of the bone.
Yeah. I've heard of that before. I know that
Is
one.
that anything like infrared rays?
I'm not sure if it's infrared that would be an application.
Yeah.
I don't know. That's a good question. I'm trying to look at the other ones to see which one it would fall into. But I've had that done to me. Because I remember when I had to go to physical therapy, I had to get my shoulder worked on. And after a while, they would hook up like a bunch of nodes. And it would cause my shoulder to kind of vibrate. And in a sense, it would end up being like a massage from the actual nodes that were on there.
This is kind of unrelated, but when we were talking about sonar before, yesterday my dad was telling me, he was really excited. He's
Oh, there's
a blind
none.
guy who learned to like click his tongue a certain way, and he
Yeah.
could like use sonar.
No way. So he would click his tongue a certain way, and based on what he heard back, he would know where something was.
Like that's how good that was. He could ride a bike. This guy she's talking about.
That's so cool. I never knew that. It's like taking what bats do and really applying it. Oh my gosh. Very cool. All right, let's go to visible light, obviously. Visible light, you should know Roy G. Biv. Okay, Roy G. Biv, red, orange, yellow, blue, green, indigo, violet. Okay, you should know your colors by now. Red being the largest wavelength, violet being the smallest. And once you get above violet in frequency terms, you get to ultraviolet. You notice? Violet is the highest frequency. Take a look here, please. Highest frequency is violet. Lowest frequency is red for visible light. Once the frequency goes above violet, it becomes ultraviolet. Once it goes below red, it becomes infrared. Hence the names. Are you realizing that? Infrared means vibrations or frequencies below red. Ultraviolet means above violet. Just
Are we going to have to memorize this chart?
no. You'll be given. Okay, you'll be given either information. You should know like simple applications, but as far as these numbers, definitely not. Definitely not. UV light, okay, sterilizing medical instruments. You ever seen that before? Okay, when you get like a work done by the dentist, okay, the dentist doesn't use the same instrument on you. They send it back in, they sterilize it and send it back to them. Or they have their own thing at their center where they can sterilize it. Fluorescent materials and minerals, you can see that if you take forensic science. Sometimes use fluorescent light to see if a drug is actually a drug. Like LSD will have fluorescence in the actual particles. And we looked at a bunch of different like not real drugs obviously, but like imitation drugs that they can make and send you for forensics. And we saw this year that when you shine a fluorescent light over them, or like a black light, you see the fluorescence come from it, which makes sense that black light is between violet and UV now. X-rays, obviously, for examining bones, teeth, vital organs, and then treatment for certain types of cancer. And then gamma rays. Okay, gamma rays. Now this is really cool. The one thing I like about gamma rays, because they are so small in wavelength, you can use them to detect structural flaws in buildings. Okay, so you can actually use them. You send gamma rays, and what it can do is send either a ray back to it, give you like a 3D print of it, and look for like little cracks in the structure. So when those waves travel through the building, it can identify if there's like, a small crack that might propagate to cause like a major failure for that building. And then treatments of cancer, and then food irradiation. So if you want to get radiation out of food, the food that has a radiation poisoning in it.
And it has a large wavelength that's like that, right? And when it's small, it's just like, if it's like...
A small wavelength just means it's short in distance, yeah. And it's a high frequency. So like a long wavelength would be like that. A small wavelength would be like this. Now this is wavelengths on the order of, 10 to the negative 5 nanometers, which
But the amplitude.
you wouldn't even be able to see it with a microscope at all.
But the amplitude can still be really big.
Amplitude can be
super
big or
tall,
small.
and-
Yeah. So you could have a tiny wavelength, right, that's short. You could have the same tiny wavelength that's short with a big amplitude. It's still the same wavelength, it's just the amplitude that has changed there. Okay? All right, let's go to the next slide. So what we're going to use here, first of all, is the knowledge that the speed of light is a maximum speed at which all energy, matter, and information in the universe can travel. Okay? All of it in a vacuum. You cannot travel faster than this. This is a number that is given, but you definitely should memorize it. Okay, it's given on your formula sheet at the bottom with the other constants, with G. But you really should memorize this because you're going to use it so often. Let's do a quick analysis of how fast light is, because people don't realize how fast light actually is. Okay, so I need you to do some work for me. So somebody who wants to go to Google real quick. All right, James, you got it? All right, Google this, James. 2,500 miles converted to meters. So just write 2,500 miles to, and then put an M. It'll convert it to meters for you. Give me a length in meters. This is the distance across the U.S.
Okay,
Approximately 2,500 miles.
23,360 meters. 4 million.
Okay. That's the distance across the U.S. All right? At a velocity or speed of 3 times 10 to the 8. Remember, velocity equals distance over time, or displacement over time. If I wanted to see how long it would take for light to travel across the U.S., I solve for t by taking x over v. So James, I want, or anybody with a calculator, take this number here, 4023360, and divide it by parentheses 3 times 10 to the 8. See what you get. Take the number James gave us and divide it by 3 times 10 to the 8, and see what you get as a number. How do you do? Or when you divide by any quantity, I always say parentheses. Technically, you don't need it if you use that E symbol, but if you wrote 3 times 10 to the 8, you need parentheses around it, so it divides by that whole quantity, not just 3, and then multiplies by 10 to the 8. Okay, because PEMDAS, it will divide by 3 and then multiply.
Is that right?
What do you got?
0.013.
0.013, let me take a look. 1, 2, 3, 4. Yeah, because the distance is smaller than the speed in numbers, so 0.013. That's in seconds. That's how long it would take light to travel across the U.S. Think about how fast that is. It's incredible. That's how fast the speed of light travels. Now, obviously, if I shine a flashlight, it's not going to make it there. Because we're not in a vacuum. Okay, the wave will not carry forever. And in a moment, we're going to see how brightness is affected. But if you send an EM wave, right, from New York to California, and you're chatting with somebody online, how long is that EM wave going to take to get there through the fiber optic cables? Less than or around 100th of a second. That's why you can Skype and stuff internationally. That's why all that kind of stuff works. Do you realize that? It wouldn't work if this were not true.
Are they gonna make vehicles that fast with it?
It would not be possible. Because people would, the matter or the force on your body would be so great that it would cause deformation in your body. You wouldn't age, you would stop aging, it would be crazy. Not necessarily melt, but you would deform.
Wait, what do you mean you said stop aging?
I can't go into detail. Anybody, if you want to read more about black holes and gravitational fields, When you get toward the speed of light, technically speaking, you go through a relativistic age change where you wouldn't change in age at all compared to other people. It's really weird. If you want to read more about this, Brian Greene writes a good book called The Elegant Universe. And he talks about string theory and stuff, and that's one of the mentions in there with the speed of light. It's also mentioned in that book series, Ender's Game, that I hope to mention. They talk about the speed of light. They do, yeah. And that's a really cool book. It's a little bit weird, the sci-fi behind it.
Would you technically never see them?
Yeah, but your body would not be able to withstand the force. So it's like yes and no. You wouldn't in one sense, but you would in the other sense. It's a little bit more than that, yeah. But the idea I want you to see is this, folks. For an EM wave to travel across the U.S., it takes 1/100 of a second. Okay, that is why you can communicate like this stuff that we do nowadays. That's why you're able to video chat somebody that's on the other side of the world with no problem at all. Okay? Does that make sense? Now, you're not necessarily sending a wave underground the whole way. What are you really doing? Anybody know? Where's the wave coming from your computer? How's it getting to their computer?
It's going to a bunch of other computers.
Satellites.
And then it goes up to a
Satellites.
satellite. Okay? There are geosynchronous satellites that rotate with the Earth. So literally, there's a satellite right above New York right now that moves with the Earth as it rotates. It moves at the exact same velocity as the Earth's rotational velocity is. So it stays above New York at all times. Geosynchronous is the name, meaning synchronous with the Earth, or geo. So if the wave gets sent up to the satellite and then back down, it's going to be traveling a longer distance, but it takes such little time that it can still do that. James?
So like which, this is completely unrelated, but like which computer information would be sent to a satellite as opposed to via an undersea fiber optic cable?
Well, coming directly from your computer, he goes to your router, or transmits wirelessly. Your router then transmits through fiber optic cables, which go to somewhere else, which I'm not actually sure where that would go. But at a certain point in time, it needs to go to a satellite. Because you can't, like, I mean, for example, James, you're not going to be able to transmit a signal from here to China underground, right? It doesn't make sense. There's no cables that are carried from here to China. So you have to go to satellites. So I'm guessing after a certain distance, but, I mean, even leaving your house, you're going underground or using cables. But at a certain point in time, that signal is going to be transmitted to some sort of satellite. I'm not sure. I struggle with this because E&M was not my field in college. So I'm not sure how to answer that. But you can research a little bit and let me know. I'd be happy to discuss it with you for sure. Okay? But the idea here is that EM waves are all traveling at the speed of light. All EM waves are traveling at this speed. Is that clear? Okay, so the velocity of a radio wave, the velocity of a microwave, of a gamma wave, they're all the same. This is the speed, or this is the velocity here. An example now. The FM radio band extends from 87.5 to 108 megahertz. What are the shortest and largest wavelengths in this frequency range? So we're going to come up with our answers, and then we're going to go back to that table from before to show that our answer is indeed correct. So we've got a small frequency and a very large frequency. The smallest frequency allowable is 87.5 megahertz. I'm going to write omega min, meaning the minimum frequency. The largest possible frequency on a radio is 108 megahertz. And that's what we'll call omega max. This is the FM radio, obviously. Yeah? And we'll convert it to hertz, but you know what we'll start doing is we'll start just using scientific notation on our calculator. So instead of writing 87.5, we'll write 87.5 times 10 to the 6 when we use a calculator. Okay? Mega, the capital M, is times 10 to the 6. Kilo is times 10 to the 3. Giga is times 10 to the 9. Those are the ones at the beginning of the year I told you you're going to need to know at the end of the year. Those are the 3. Tera is 12. Okay? It is, I'm sure. I'm 100% sure. A terabyte is 1,000 gigabytes. A gigabyte is 1,000 megabytes. A megabyte is 1,000 kilobytes. And technically speaking, it's like 1024. They're powers of 2. But it's on an order of 10 to the 3rd each time. So that's how I know it's 10 to the 3rd, 6, 9, and 12. Minimum, maximum frequencies. We want to know the longest and shortest wavelengths. So how many times do we have to do this problem? Twice. Remember how I gave you the homework problems that had parts A, B, C, and D? Same idea. This is like part A, this is part B. what's our velocity going to be in this equation? Remember, velocity equals omega times lambda. What's the velocity for all EM waves? What did we just say?
3 times 10 to the 8.
Yeah, so that's a constant. So here's our formula, but we can replace the velocity with 3 times 10 to the 8th. Let's solve for lambda in this formula. Lambda equals velocity over omega. So we're going to do this twice. Okay? We're going to calculate a lambda first using 3 times 10 to the 8 over 87.5 times 10 to the 6. That's the first lambda we'll get. Then we'll take the next one and do 3 times 10 to the 8. I'll do it in red. Over 108 times 10 to the 6. That's the second problem. But do you see why the generic solution is important now? You don't need to solve this twice. Solve it once for lambda, and then just plug in the different numbers. Only the denominator is changing. Here's something interesting. When you have a minimum wavelength or frequency, when you have a minimum frequency, what do you have for wavelength? They're inversely related. Yeah. So when we use 87.5, we're going to get lambda max, even though we used omega min, because they're inversely related. And you'll see that the numbers, one will be bigger than the other. Okay, but just so you can know that. Again, when you use omega min, the smallest frequency, 87.5, you're going to get lambda max. Because as omega goes down, lambda goes up. Remember, they're inversely related. You can see that right here in this formula. Take a look at this formula. As this quantity increases, this is going to go down because you're increasing the denominator. More people are eating the pizza, each person gets less amount of pizza. So as this goes up, it goes up from here to here. This has to go down. So this is the max and this is the min. What do you get for your numbers? Use parentheses, please. What do you get for your first one here? What do you get for the first one? For the first one, I'll tell you now, it will be a number greater than 1.
I got 3.43.
For lambda max, very good. 3.43 is correct. And that's in meters, remember? Because this is in, ready? Meters per second over hertz, which is 1 over seconds. Seconds cancel, leaving behind meters.
Is the second one 2.77?
It is, very good.
Would you be able to?
Well, 2.78, I think, if you round it.
2.77.
Would you be able to cancel exponents instead of just do
Yeah, so the 8 and 6 can reduce to 2. You can do 3 over 87.5, and then multiply that times 10 to the 2.
so if there's 300 divided by 87?
Wait, but it's times 10 to the 12.
Yeah, you could do this as 300 over 108, and that gives you 2.78. Absolutely. Does everybody remember how to use scientific notation? Press second, and then press the... Because you didn't put parentheses around the 87.5 times 10 to the 6. Okay? Make sure you put parentheses. I want to make one more thing before you go, real quick. The last thing, for brightness of light. It is inversely proportional to the square of the distance. For example, if I hold the flashlight here, and it's 2 meters away, if I double the distance, the brightness is going to go down by a factor of 4. It's the square. If I were to triple the distance, so here's the distance here, and now I triple the distance, the brightness is 9 times less. This last part here. That's all this is saying. Quickly read through it on your own, okay? You can still do this part. What's that? It's all about ratios of one to the other. It's not actual distance.
It's 14.
Relative distance. Hold on one sec, James. Tonight, you need to work on, let's see, what's today? Wednesday?
Homework from
Problem
yesterday.
set.
12.
Problem sets tonight, and I'll make the homework from 14.1. Oh no, wait.
12.4.
What do you guys have tomorrow? Do you have double or single?
Double.
Double. So problem sets are due for you guys tomorrow.
Wait, what?
Okay? Or they do Friday. Friday. Homework from, I'm a little
Yesterday.
sidetracked.
Homework from yesterday.
Homework from, we have activities. Why are we all rushing out of the room? Give me a second to talk. 12, 12 for homework from yesterday is due tomorrow. Okay? Problem sets are due Friday. 14-1 will be due on Monday when you take your test. Okay? Thank you.
Is this the last section before?
Yeah.
This is the last section. Tomorrow we're reviewing for one period, and then we're going to do another lesson, but completely separate.
I meant like, what if
12-1, 2, 3, 4, and 14-1.
what if D is less than 1? Like if it was 0.25, then if it was 0.5, it'd be 0.25 is the square.
This is the relative distance, though, James. That's what I'm trying to say.
Relative.
It's not the actual distance. So, like, between from one spot to another, for example,